So now you will listen to Dima talking about Dragonflow. So Dima, the stage is yours.
Thank you. Good morning, everyone. Today I'd like to talk about the Dragonflow project and our effort to make it into this open platform for network services. First, about myself, as I was introduced, my name is Dima Kuznetsov. I work on the Dragonflow project. I'm the core developer there. I work for the cloud group for Huawei's Tel Aviv office. And I'd like to start by talking about software-defined networking. Now, I thought for a while, how can I introduce software-defined networking? Because it's quite of a broad concept, but basically I came to the definition of where we have a specific and a unified interface for controlling and configuring the network fabric in the data center in the infrastructure. I think this definition would be quite suitable for this presentation. And what usually it means that we have a central component. This may be a single server or a cluster of servers that you can query or request changes to the network topology through this service. And it will take care of performing this configuration request. And it basically allows you to separate the network configuration problem from the actual forwarding and physical access problem, where you want to configure a specific topology of the network, and you don't have to bother with going to each of the switches and the routers and configuring them accordingly, and you have this kind of software-defined network solution doing this for you. And what this allows us to do a lot of time is to do a thing called networking virtualization, which can be thought of just like a regular virtualization, where we have our physical machines and we have the virtual machines, and we can have several machines on a single physical host, and we can have different kinds of machines on a single hypervisor. And networking virtualization allows us to do just about this. We have our data center or our infrastructure, and we may have a single physical network there connecting all the machines. But we may want to create an illusion for the VMs that we are in different networks, maybe different addresses. Maybe we have two VMs on different hosts, but we want to create an illusion that they are connected one to another directly. And the SDN allows us to kind of create this illusion and show the VMs or the containers this virtual topology instead of the physical one, where they can see how the data center is connected, how the hosts are connected, and how the switches and the routers are configured. Okay, and as we talked earlier, we have this network network service configuring network fabric, the routers, the switches, and one popular way to do this is through an open flow protocol. An open flow protocol is an abstraction for configuring network appliances, where each appliance is represented as a bridge or a switch or a router, and it is basically a state machine for packets coming in. And the states are separated into tables, where each table has a collection of flows. And a packet coming in will land at some table, and the switch will apply a specific flow to it, and then if it decides it needs more processing, it will apply another flow, maybe from another table or the same one. Now, each flow is composed of two things. A flow is a match, which means what packet this flow should apply to. This can be on any from OpenFlow allows you to do this based on the L1 through L4 levels. You can say I want all IPv4 packets, or maybe I just want TCP packets targeted to port 80. Or maybe even I want all the non-SYN packets coming into the switch. When a packet arrives to a specific table, the switch will go through all of the flows in this table, sorted by the priority, and try to see the first one that applies to the packet. Now, the second part of the flow are the instructions. And the instructions basically say how the packet should be handled if the flow matches the packet. And they basically do, I think, three major things. One of them is modify the packet themselves. You can request a packet modification. Say, I want to replace the source MAC address of the packet. You can modify the the state of the packet and say I want a next table to be table 20, or maybe I want to set some local register of the packet, which is a state that the packet carries with itself through the switch. And you can say that you want to drop a packet or output it to a specific physical port of the switch. And this allows you basically to implement a lot of low-level networking functionality in the switches. Like you can say that you want to receive a packet and see if it's on a specific network, like by examining its VLAN ID, and then deciding what ports it can go out to and what ports it cannot. So this was quite a quick introduction to OpenFlow. We'll come back to it later. And I'd like to talk now about Dragonflow. Dragonflow is an open source project implementing a software-defined networking controller for OpenStack and Kubernetes at the moment. It is built on a few major principles. We wanted to try to make it as lightweight as possible and quite as simple. So if you have a small deployment, it won't be too much of a burden to run Dragonflow there. But also we wanted to make it quite scalable. So if you have a huge deployment, you can still try to use Dragonflow and not being limited by its architecture. And additionally, we try to make everything pluggable. So we don't know how the deployment will look like in the end. And you might have a single data center and a very converged infrastructure, or maybe you have a distributed infrastructure, maybe you have just a huge amount of nodes, and you may want to use different features for different kinds of deployments. So we try to do a lot of things in a pluggable manner. And finally, we try to distribute a lot of stuff to the nodes, meaning that many of the services we try to provide them in a distributed manner. For instance, one of them is DHCP. If you look at a traditional DHCP implementation in Neutron, you'll see that it has a network node running a DNS mask, answering all the DHCP requests from there. So if you have 10 machines and one network node, all of the DHCP requests will travel to the network node, and if it is unavailable, then none of the machines will be able to get DHCP. And we try to avoid this kind of points of failure by pushing the functionality towards the VM. So one example that we try to do is our DHCP server is handled by the controller itself. So if a packet of DHCP request comes out of the machine, then the controller will capture it, see it's a DHCP request packet, and craft a specific reply packet and send it back. So there's no dependence on an external server, and the only reason that you won't get a DHCP request is that the machine is down, so the VM is down itself. So there's not much to lose there. And some more trivia about Dragonflow. It is a 100% upstream and open source project. It was an official project within the OpenStack community. It was initiated by Huawei a few years ago. It's in the OpenStack since a kilo release. And it is led entirely by community and not by product. Okay, so here is a high-level architecture overview of Dragonflow in an OpenStack Neutron deployment. We have three major components here. We have the Neutron server at the top in the middle, in a nice orb there, where we have our Dragonflow management code. In the center, we have the Dragonflow distributed database. And on the sides, we have the compute nodes running the virtual machines connected to the OVS bridge, and Dragonflow controller controlling each local OVS bridge. And as I said earlier, Dragonflow can also be used in a Kubernetes environment. So here as well, we have the control node at the top in the middle, where we have the Kubernetes API, and another service called OpenStack Courier, which is an OpenStack project for interfacing and allowing networking from Neutron or other providers towards containers. And inside Courier, we have our Dragonflow drivers that translate the requests from Courier to Dragonflow. And those two are basically on the same orb, but they don't have to run one next to another. They can be on different machines. The main point is that we have the Kubernetes API, and then we have the courier service subscribing to Kubernetes API events. So they don't have to run together, but they act as a single unit for this purpose. And then again, we have the Dragonflow database in the center, and on the edges we have, now we have pods instead of VMs, connecting to an OVS bridge instead of Linux bridges. And then we have our CNI and kublets running on the compute nodes alongside with the Dragonflow controller controlling the OVS bridges. Now, if we look back into a typical OpenStack Neutron deployment with Dragonflow, we'll see that on the lower level we have the Dragonflow part in the Neutron server, and we have the Dragonflow part on the controller, and they talk one to another through a distributed database and a publish-subscribe interface. And one of the points of applicability that I tried to talk about earlier is that we try to avoid being restricted to a single set of database and a PubSub mechanism. So we abstracted everything away through a driver layer. And there are really several drivers that we support and maintain in our code, like Redis or etcd, and I think Zookeeper and Cassandra. But what is common to all of those interfaces is that they are quite simple key value stores. So you can come up with your own driver if one of the databases does not scale well enough for your deployment or does not answer specific requirements. So implementing a new driver is basically a matter of writing a few simple functions to store values and retrieve values from the database. And same with the PubSub mechanism. We use PubSub to facilitate faster updates between the management part and the database and the controller, excuse me. And again, we can use the distributed database mechanism here to implement the PubSub functionality, or you can use any other kind of other database that you have deployed in your environment, or you can use a no broker solution at all, like ZeroMP. The PubSub interface itself is also abstracted behind drivers, so implementing a new mechanism should be quite simple. On the higher level of functionality, we have the Dragonflow drivers and service plugins inside Neutron. Each one of those tiny little cubes at the top is a driver or a service plugin in Neutron that handles a specific segment of functionality. For instance, we have the L2 and the security groups handling translation of incoming networks, ports, and security group events, and translating them into Dragonflow actions and state. And we have other plugins for handling L3 routers and quality of service and service function chaining. Each of those cubes is a stevedore entry point, so it is dynamically loaded by Neutron, so you don't have to write those stuff directly inside Neutron code. You can just register it externally, install the plugin, and set the configuration, and it will be loaded. On the bottom, we have the Dragonflow controller here, connected to an OVS bridge that is connected to our VMs in the containers. And inside Dragonflow, we also have those tiny cubes with names on them. Those are Dragonflow applications. Dragonflow controller itself is basically a mechanism for distributing events coming up from the Neutron server or any other kind of northbound API into the applications on the Dragonflow controllers. A major differentiation from the Neutron's Open vSwitch implementation is that we don't distribute flows and actions through RPC. We push policy towards the controller. So each of the controllers sees the complete state that it requires to set the data path and modifies the data path according to the state that is required. For instance, if such events that coming in from the server can be a new port is created, and then the controller itself has to decide how the data path has to be modified to accommodate this port. And as I said in the beginning of the talk, one of the points that we try to address is to make Dragonflow a more of an environment or a platform so you can introduce your own network functionality, because with SDN solutions, a lot of time, the data path is kind of a black box, and you don't have much of a direct control over what happens there. You may be able to configure it through maybe through runtime or configuration, but you don't have real control of what happens to the packets inside the data path. And we try to actually to enable this kind of change, so because no deployment is the same, and you may have to tweak your data path to make stuff more fast or maybe more efficient in your data center. Now, from the pluggability standpoint, as I said earlier, in the Neutron server, a lot of the plugins and the drivers are basically stevedoor entry points. And we didn't have to do a lot of there because we kind of got this for free from the way that stevedoor works. By using configuration values, you can enable or disable specific functionalities inside the Neutron server and introduce any of those boxes and maybe other boxes down there to do specific functionality. Now, on the controller side, as I said earlier, we have applications. A specific application is responsible for really a small piece of data path functionality. For instance, we have here port security. Port security is a quite simple application. It is responsible for a specific table where packets go through when they are coming out of a VM or a container. And this port security application will just filter all the packets that match the source IP or MAC address of a specific port. So the VM will not be able to MAC spoof its packets in the bridge. And again, we used stevedoor here to allow dynamic registration of applications. So you can write an application, put it outside of the project, and it will be loaded and started by Dragonflow as if it were one of the core applications. So stevedoor really helped us out on this aspect. And if we are going to talk a bit more about Dragonflow applications, there are basically kind of three major types that can be classified into. We talked about OpenFlow earlier. So one simple example of application are applications that just use flows. So the application receives events from the database, and it will modify specific tables to match to the policy described by the table. This can be a port security, as I mentioned earlier, that it sees a new port created and it will create a new valid flow in the port security table. It can be routing that sees that a new router is created and will create a new routing rule in a table. And it's kind of the best applications in terms of performance because the packet will be serviced entirely by the OVS, and the packet does not have to travel anywhere. And the problem is really constrained into this specific bridge. And some examples, as I said earlier, are port security, L2 forwarding, routing, responding to ARP requests, and ICMP pings. Now, second type of Dragonflow applications are a bit more complex. One of the things that OpenFlow allows is to send a packet to the controller of the bridge. So the second type is kind of applications that install flows, but also send packets to the controller for handling. And this can be an issue for both from both the control plane perspective, because your controller is now also dealing with the forwarding and data plane a bit. It has to process packets. And also from the data path perspective, because now your controller has to... The packets have more latency because the packet has to go to the controller has to treat it and send it back to the bridge. But it also allows you to implement a more complex functionality like the DHCP server. So the DHCP application will capture all the DHCP discover and request packets coming out of a virtual machine. And then it will see what port it is coming from and craft a specific reply packet and inject it back into the bridge. And there are other examples for why this can be useful. And finally, the last type of applications are kind of the most complex, where we have the application that installs flows, but we also deploy an external service on the side. We attach an interface to our switch, and we configure an external service to listen on this interface, and then we install the flows that route specific kinds of traffic into this service interface. And it allows us to do a lot of much more complex things, like a metadata service, which is basically a HTTP proxy for some Nova API, or maybe a DNS lookup, or a load balancing by deploying HA proxy alongside the Dragonflow controller. And it basically allows us to take advantage of the protocol stack on the hypervisor. Because in the previous slide, when we are packetting in our packets to the controller, we had to deal with the protocols ourselves. And if you look at HTTP requests, it's quite harder to do this because there's a lot of state. We have to implement TCP in our controller, and we have to implement HTTP on top of that. And by deploying a sidecar service and attaching it to the bridge, we can just take advantage of the hypervisor TCP stack and use that for the controller. But also, there are also downsides to all of this, because now we have to make sure our service is alive as well. We have to deploy it, we have to configure it. We have more moving parts on the compute node, and we have to make sure they are live and behave well. And now, kind of the problems. All three types of the applications, they were doing one thing in common. They were installing flows. And as we saw earlier, OpenFlow is quite a low-level API for a switch and forwarding configuration. So this works well enough if you have your own applications, and you can kind of coordinate what tables will you use and what registers you will use. And you will make sure that there's no application that steps on the toes of another application. But this won't work well if you want to have third-party applications or maybe pluggable applications where you have two applications that have no notion of one of another, and they want to use the same flows or maybe the same registers. This will cause trouble. And not just pluggable applications. We have some of those woes inside Dragonflow code itself. We have our table 55 that handles L2 forwarding, and then we have some flows installed there by the forwarding application, but also some flows installed by the L3 routing application and some flows by the DNS application. And now we have to coordinate the priorities of the flows of each application with all the application using it, and we'll have to make sure that when we delete flows, we don't delete flows from another application. And this basically means that a lot of care should be taken when adding and changing stuff there, and debugging and troubleshooting is much harder when stuff don't work. So it's really not a nice way to let people write pluggable applications but then run into this kind of trouble. So what we came up with, we decided that we are going to introduce something called application specifications. So each application will specify what kind of interface it exposes towards the data path, and kind of wrap each application into a black box on the data path, where the application itself will be responsible for whatever happens inside this black box, but nothing of what happens outside. So the basic specification of an application looks like how many tables it wants to use and what registers it is going to use to implement the functionality, and what are the application entry points and the exit points. Now, an application entry point is basically a callback into something what we want the application to do. For instance, here we have a security group example. A security group application enforces network policies on the cloud network. So we can have a network policy saying that for this VM, we want to allow incoming ICMP packets, but we don't want any of UDP or something like that. And here we have two entry points and two exit points. Now, ingress entry point means that all packets coming into this entry point will be serviced as if they are ingress for a specific VM. And the egress entry point will be handling all the packets coming out of those specific VMs. So if we want to use this kind of black box, we'll have to wire all the packets coming out of the VM to the egress port and the coming into the ingress entry point. And the exit points are basically the same, where each application is kind of taking packets in and outputs them out. So if you have several entry points, it may have sense to have several exit points. But the relation is not always one-to-one. For instance, we may have L2 application that does forwarding. So we may have only a single entry point, but we have several exit points, for instance, one for unicast packets, and also one for multicast packets. And along with the specification, we also introduced a more strict semantics for applications. So this won't be for nothing. We decided on a set of rules that an application should abide by. And one of them is, we said earlier that we require application to declare all the tables it's going to use. So an application can only really interact with its own tables now. And it can only access the registers that it declared it will use. It will only go to between tables of its own, or maybe to one of the exit points. And if we talked earlier about this packet in, packet out to the controller functionality, then the application won't intercept packets from tables that belong to other applications and won't inject packets back to tables of other applications. So basically it confines itself into this kind of specification black box. And now if we kind of zoom out of a single application, we still have the data path, and now it's built of those boxes. So the controller itself is responsible for connecting all of those applications between themselves. And on this level, the connection is quite simple. There's no branching. Each exit point goes to exactly one entry point. And the controller also is responsible to swap the registers between the applications. So if one application expects some value to be stored as rec 5, but other application expects it at rec 7, the controller will be responsible to move it between the registers. And this also allows us kind of neat functionality that now we can validate a lot of stuff about the data path. We can see if there are any maybe unwired entry points, or maybe applications that are at all not unreachable, that are not reachable at all, or maybe we are consuming a variable in application A, but no application before it ever generated it, so we can run into some trouble there. It allows us to assert more correctness on the data path now that we have those kind of contracts between the applications. And finally, to allow all of this integration between applications, we wanted to make all this wiring configurable. So the controller itself, as we said earlier, it handles the actual wiring between an exit point and an entry point, but it does this by reading the configuration. So if you want to plug in a new application, you just have to add it as a stevedore entry point, and you go to the configuration for a data path, and you kind of insert it on one of the edges, or maybe several ones, and you don't have to modify the Dragonflow code itself. What we try to achieve here is that we really try to be able to write a specific feature top to bottom from the management to the data path itself without being required to actually go into the Dragonflow code and modify internal functionality. And that's about all I have on this topic. We are an open source project, and we'd be happy if you see you participate. We have an IRC channel. It's hash openstack-dragonflow at Freenode. And we have weekly meetings. One actually the times are bi-weekly. We have one for the Pacific time zone and one for the US. And that's it. Thank you. If anyone has any questions, I'll be happy to take them. Yes?
Do you have plans to implement load balancers as a service?
Do we have plans to implement load balancers? Yes, actually, we have a specification and a design already done, and we have someone working on that right now.
And how do you plan to do it?
I think
Do you have an idea? Being sent, L7?
No, at the moment we don't plan to do L7 right off the bat. We want to do L4 first. And I think we will do also maybe the proxy. I don't know yet. Anything else? No? Thank you.